So welcome everybody. We're going to start in a minute or so. We already started the recording, and yeah, so we'll just wait for another minute before we start here. Hello, everybody. Welcome. And just to let you know that next week the UK time is changed, so people who are overseas, just follow that. The best way I find out the time is just to go into Google and sort of find out what the time is right now, and that's the way I find the UK time right now, and that's the best way to do that. So, okay, today's session may not be so long, and this being the second last session, so we already got 14 people, which is great, and the last session is the one coming on the Sunday. So the plan for today is that first of all, I'll present autoencoders, which is the last subject, one of the last subjects we need to cover, which is unsupervised learning. And then we are going to, Aisha is going to present about the convolutional neural network, which is also the last subject from our point of view, which we are going to cover from the notebooks, because as I said, there are four key algorithms we are covering, which is the regression, classification, MLP, and CNN, and that mostly covers the key areas of machine learning and deep learning, and this was the objective right from the beginning, so that's been the goal, and Aisha is going to cover the CNNs today, and the next session, we will more or less keep it quite interactive in terms of answering questions, looking through them, and so on and so forth, and we might have Kauthar for the next session to cover that. So this will be the plan overall. The next session will be again a wrap-up session, and this session will be hopefully it will depend on how much you guys have to present, but I will start in any way. First of all, presenting the autoencoders, which were the last major subject left before we go into iShift for CNN, and then whoever wants to present the code. So I'm just going to start sharing in a minute. Yeah. I need to unmute myself. Yeah. So you should be able to see my screen. And now I'm going to cover the last subject, which is autoencoders. And then after this subject, we will go back and to start to look at the code from CNN, and then we'll take some code presentation from you guys to see where we are at. Okay, good. So this subject is the last sort of the unsupervised for deep learning. And the reason why that matters so much is because it's a hot topic at the moment, with so much work going on around unsupervised algorithms for deep learning. But initially, it wasn't such a big deal. Autoencoders was something which started, and people didn't quite know what to make of it. So let's start off with autoencoders. The autoencoders is an unsupervised learning technique, and it uses neural networks. It's a deep learning technique. So last time we saw clustering, which was unsupervised learning technique for machine learning. And the basic idea of an autoencoder is to introduce a bottleneck which forces compressed knowledge representation of the original idea. And the idea basically is to capture the structure in the data if one exists in a bottleneck. And once it's identified, the underlying structure can be used for other things like anomaly detection. So how does it work? So in the case of an autoencoder, what you're looking for is the reconstruction error. Remember that unsupervised learning does not have labels. Yes, so when you don't have labels, we need to do some other kind of techniques or strategies to find out some detail from the data. If you have labels for the data, then you train it using label data, and with the label data, you can make some predictions, or classifications, etc. But when you have unsupervised learning, you do not have a label, and that's a key characteristic. So what you do when you don't have a label, you do reconstruction. So this is one of the strategies. A reconstruction error, as the name implies, represents the difference between the original and the reconstruction. So this is the whole point, that if you are able, with a little bit like GANs, if you look at the GAN, the idea of the GAN was that when you have reals and fakes, and at the moment when you are able to make such good enough fakes that you fool the, the sort of the discriminator, then you can effectively throw away the discriminator, and then you have a very good fake generator. Yes, so this is the point of a generative adversarial network. So again, to recap, in the generative adversarial network, you have both a generator and a discriminator, and objective of the discriminator is to effectively act as the sort of the police, or the art expert, so to speak, and an objective of the generator is to generate enough sort of copies of something such that at some point, based on the feedback, the you are able to create good enough fakes, and at that point then you throw away the discriminator, and then you have a good enough fake generator. So if you extrapolate the idea here in autoencoders has something called a reconstruction error. The idea of the reconstruction error is you have something and you try to reproduce it, and if the reproduction is the same as the original, then you know that you can make good enough sort of something is valuable about that. And the key thing is that the reproduction is based on a bottleneck. Yes, so the bottleneck means that you force the input into a smaller sort of a artificially smaller construct, such that it forces to create a smaller representation in the original. And when you have effectively managed to reconstruct it such that the reconstruction is same as the original or similar to the original, you are then able to say that the compressed representation is valid. This is the basic idea behind it. So how does that work? In the neural network, if you compare a typical neural network, it looks like this, but an autoencoder introduces the bottleneck. The bottleneck means that the intermediary layer is smaller than the input and the output layer. So what happens in this case is, unlike in the traditional neural network, where the number of neurons are the same across the whole neural network, in an autoencoder the number of neurons are much smaller. And once you have that, what you are in a situation is that you are creating an artificial bottleneck. An artificial bottleneck based on the hidden layer compresses the input layer and makes it smaller. And once you do that, your goal then is to compress it and to uncompress it such that the reconstruction is similar to the original. Once you are able to be satisfied with the reconstruction, you can then say that your reconstruction is effectively that the bottleneck is effectively valid. This is the thing. So the smaller compression layer, compression which is created from the bottleneck, is a valid representation of the input if your reconstruction is minimized, and that's the basic idea behind it. So the autoencoder manages the trade-off. So obviously the trade-off between sensitivity to inputs and insensitivity to inputs. And to do that, you have to construct a loss function which represents a regularization function within that. So this basic idea of an autoencoder works in this way, that you have an encoder and a decoder, and the encoder creates a smaller layer, compressed layer. The decoder tries to decode it, and once the minimized errors are minimized, sorry, the deconstruction is minimized, you know that the compressed representation you have is valid from that perspective over there. So this is something similar to PCA, but it is non-linear. So PCA also generates a representation, a hidden pattern, but autoencoders are able to generate or able to work with non-linear patterns within that. So it's a sort of a similar idea to PCA. And you can see this in a diagram like this, where an autoencoder is able to sort of understand non-linear patterns much better than a PCA does. The PCA typically looks at linear sort of demarcations between data. Then there is the question. Okay, I'm going to take some questions now because I think that this is sort of enough explaining of the basic concept of the autoencoder. If anybody has any questions at this point. Okay, so anybody has any questions? The basic idea of the autoencoder, which we have. Okay, there is something in the chat. Let me see. Okay, audio problems. No, that's fine. No, there's no audio problems with that. There is that use performance boost as well. So not really performance boost. The main idea of autoencoders is simply the fact that it is basically a compression mechanism. It's not to do with performance. It's to do with the fact that you have an input and you reduce it to a small. It's like saying that if it's like saying that I have an input, I compress it and I uncompress it. And if the uncompression is very similar to the original one, then I know that my compression works. And then I throw away the uncompressing mechanism so that I then keep the compressed version of it. So this is the basic idea. So yes, you have a question, Prashant. Yeah. Yes, Prashant.
Yeah, the same question you
Yeah.
answered it.
Okay. Okay.
Thank
Fine.
you.
Fine. Good. Good. Okay. Then that's good. Yeah. Thanks. So Sonal, yes, you have a question. Yeah.
I can understand how this can be used for images. Is there an application for text as well for this?
There is a whole bunch of things around text, but not necessarily autoencoders, as far as I'm aware. The whole area around text is happening around natural language processing and around the transformers and so on and so forth. So there might be something with autoencoders, but it's mostly based around the images concept. Yeah. at the
So like not really used for any text generation or something where the encoder part will generate a text and the decoder will like see if that like I'm talking mostly like for caption generation.
Yeah,
Uh,
yeah. But the point is that there are transformers which do that function exactly. And that's just what my point is that most
okay.
of the action around NLP and text is happening around the transformers world. And that's where I think while there might be something in the auto, but the point here is that most of these things are very similar.
Mhm.
So they all are sort of similar concepts which are built around each other. And yeah, so the idea is similar, which is used in some of the other things as well in the text, but not necessarily as autoencoders. Okay.
Okay, thank you,
Okay,
thank you.
thanks. Yeah. Okay. So now, since there are no more questions, I will proceed with sort of expanding more on the idea of autoencoders. So I basically shared with you just the first and the basic version of an autoencoder, which is the point we are trying to make here is the basic idea that you introduce in the neural network the intermediate layers which are smaller than the original one. So by introducing the bottleneck, you can introduce the concept of the autoencoder within that. So now there are a few other ways to create a bottleneck. The first one is called sparse autoencoders. So the idea of a sparse autoencoder is to introduce a bottleneck by reducing, instead of reducing the number of neurons, you keep the same number of neurons, as you can see here, the same number of neurons in each layer, but you drop out some of them in the middle. Yes, so in some of these cases, you have A3 is blue, but the other ones around it are sort of not that blue. So they have been removed. So you remove some of the neurons um, within that, and this is what you end up working for a sparse autoencoder. And a sparse autoencoder also achieve the same concept, that you have a neural network which you want to reduce the bottleneck for, and that's what you sort of try and do with that. So sorry, you want to introduce a bottleneck for a neural network, and that's what you try and do with that. The and the area, this is one of the areas of autoencoders which is used quite a bit, is called the denoising autoencoder. The denoising autoencoder basically works because You if you successfully if you reduce the reconstruction error, you effectively reduce the noise as well. So this is one of the functions of the autoencoder um, where it effectively functions as the denoising component as well. Because if you have noise and you feed it to an autoencoder and you make a reconstruction error, it actually looks at the salient aspect of it and removes the noise. And in doing so also functions as a denoising autoencoder within that. So in effect, the autoencoder is something which helps you to determine the underlying structure for a neural network. And the way it does that is that it introduces an artificial bottleneck. The bottleneck may be in the form of reduced number of neurons, like a bottleneck within the neural network, or you could have sparser encoders, which is the same number of neurons in the layer, but some of them have been removed with that. So the idea then is that you create a bottleneck of some kind, and it functions the same way within that. So this is the general idea of an autoencoder, but the significance of autoencoders is what it is used as a generator. And this is where it gets sort of very interesting, because as you can see, the function of the autoencoder is to find out so in the autoencoder, the bit in the middle is actually more valuable than the other mechanism is actually to find the bit in the middle. The bit in the middle is the most important one, because that's the one you're trying to represent or trying to compress, and that's what your goal is within that. So once you are able to find effectively what is called learning a latent space of the representation, then you can do other things with the latent space. So for example, you have the concept of the variational autoencoders. The variational autoencoders extend the idea of autoencoder to generate a powerful generative mechanism for producing synthetic content, which is fake content effectively. So remember that a generative model creates a new output that looks similar. The idea of the variational autoencoder means that it varies certain things in the input so that it looks different. So how does it work? So for example, if I have this person with glasses, I can actually add glasses to this person, without glasses, with glasses, or I can decrease or increase the width of something. Yes. So given a particular data, you are able to uh, effectively vary certain features with it. In this case, we have added glasses to the person, or you have decreased the width of something, and this is how you sort of start to build those ideas with that. So remember that what happens here, to look at the theory behind it, is that you have autoencoders and you have the encoder and the decoder. And like I said to you, the whole point of the encoder decoder mechanism is to find out the hidden or the dense representation. And this idea actually is very similar to including it to CNNs. Yes, so everything in AI is that sort of that neural layer is the more important bit, where it tries to find out hidden representations of something, and over time is sort of able to work them out. And that's what you kind of end up doing. So what you end up doing is you sort of look at the idea of encoder and decoder, and such that the encoding, that is the one in the middle, is the most valuable one. So the decoder is used to check the encoder, and that's the goal of these things within that. So the way, once you do that, the next thing is to find out variational autoencoders. So the way variational autoencoders work is that if you have um, if you have the latent attributes, in the latent attributes, it's able to find out certain characteristics of the input, correct? So if you have a face of the person, when it does the compression, it's able to find out in the smaller feature, it's able to find out these are the probabilities of having those features. And when it decodes it, all it does is trying to sort of recreate that. But if this hidden was a probabilistic model, then you could change features. So for example, if I were to determine that this is a smile for this person, for this boy, I could then change the smile. Similarly with Mona Lisa, I could also make it different, and so on and so forth. So all of these things have a distribution. And if the latent features have a distribution, then those latent features can be varied. And this is the whole idea of generative models, is that once you find out a compressed representation, or if you, so the first stage is to find out a representation of something. The idea of representation is the same as the autoencoders, is when you find out the sort of the bottleneck layer in the middle, it's actually finding out a representation of the original content. And then when you are able to find a representation, you can vary that if it's probabilistic, and then it changes the features, then it changes what it is. And this is what you're trying to do. So what you're trying to do is, once you find out something, you are able to change it, and that's what is called variational autoencoder. So once you have an encoder, you can change the specific features of the person, whether the smile, the skin tone, the gender, and so on and so forth, and then that looks to be quite different from the original one. And there are a number of applications of this thing. The most important one actually is anomaly detection. Because anomaly detection is generally used for most unsupervised learning techniques. And like I said to you, the reason is because you don't have the valid case. You don't have too many times, which is, you don't have too many examples of, so that you can't train it for the valid case. So it effectively becomes the sort of finding out the reconstruction error, which is different from there. Very good. Okay. So this completes the autoencoder section. And I think that any questions on this so far? That, let me see what we, okay, here we go. Oh, there are some questions here. Da, 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 da. Yeah, run length auto in a form of lossless data compression. Okay, this is fine. Thank you. It's okay. Thank you for the okay. Um, okay, so this is the conversation. It's not a question. Um, okay. Okay, good, good, good. So it's a conversation about different things, not a question. So yeah, so I think who raised their hand first? I think it was Prashant. Yeah, go ahead. Then there is Farid. Yeah.
Yeah, thank you, sir. Maybe a basic question. So for this one, you have said the encryption part, that is the blurring of image, something, and then we can decode it. So in some websites, so there are some applications where we have to confirm that we are humans, and there is some images that comes. So in that also, my question is, at that place also, this algorithm or this method is used, auto encoding.
Not necessarily, no. I mean that, so what you're talking about is when images are blurred. So the main reason for using autoencoders is to find out the representation or a compressed representation of something. And
Okay.
once you do that, there are multiple reasons why you want to do that. The first one is that once you find a compressed representation of something, you can use it as an anomaly detector, for example. So you can find out sort of if you reconstruct something and the reconstruction error is much higher, then you know that it's an anomaly. Um, that's one way to use it. The other way to use it is what I just described. The later part is variational autoencoders. So you try to find out what is the compressed representation, and then try to vary certain features around with that. The blurring of the bit is possible, but my point is there are other ways to blur images than doing something like this, which is a much
Okay.
more complex way to do it.
Okay.
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 All right. Thanks.
Yeah.
Yeah. So Farid, yeah.
The question behind the conversation was, how is the compression achieved? Is it some kind of run length coding, i.e., you're looking for runs of data that are the same, and from that you annotate a feature? How is it done?
I don't know what run length encoding is. But the compression is pretty much the same as what you do, um, as with any neural network. Yes. So for example, you have a neural network and you are trying to train a neural network using uh, any form of sort of back propagation, gradient descent, etc. Yes.
Hmm.
So we have in this case the only difference is that you have, rather than one network, you have two networks, and there is a bottleneck in the middle. So what you do is you continue to train it exactly as you would any other neural network, and once it is trained in a specific way, in such that the encoders and the decoders are working together. So for example, if I were to encode something and compress it and decode it, um, and this encoding decoding mechanism works as any other neural network. Yes, so there's no different from a traditional neural network within that training of neural network. um, and that's how the compression happens, and the only reason why it happens is because you have physically created a bottleneck within
Okay, I maybe need to look at it in more
it.
detail
Okay,
offline.
sure. Yeah,
It's just the compression is still kind of foxing me how it's done.
yeah.
And the thing with run length is that, especially for images in video, for example, what they do is they can basically guess what the reconstruct the image, because something similar is done in MPEG, i.e., you compress the image and decompress it on the other side, and part of that is recognizing common sequences of
Cool.
images.
Okay, that's fine. I wasn't aware of that.
But anyway,
um
I probably
yeah,
need to look at it
yeah,
offline because
yeah.
it's still
Okay,
a bit vague. But
cool,
thank you.
cool. Okay, no worries. Yeah. Okay, so any more questions on this so far? Good. Okay, John, what is the fundamental advantage of autoencoder compression? So, like I said, the fundamental, and there are two or three advantages. The first one is you can use it as an anomaly detector. The second one is the second part I mentioned, was that you can use it in the form of variational autoencoders. And a variational autoencoder basically is the way in which you find out a latent representation of something and then vary that latent representation based on some parameters. So this is generally how you would use that. But the concept of autoencoders is sort of similar to some of the other stuff which we have been looking at, is the idea that that most of neural networks are trained in whenever you are training a neural network, such that it's the same idea as GANs. Yes, so you create an artificial scenario, such that you find out the latent representation of something. So this is the whole idea of it within them. But from an application point of view, the earliest and the quickest way I could think about is either noise reduction or anomaly detection. So this is John's question with that. Okay, so all right. So I think if there are no more questions, then I might ask Aisha to present, and then depends on this, we'll see who else has got to present any code from last time. So Aisha, do you want to present now?
Yes, I can start it.
Good. So I've stopped presenting. So
Okay.
you can now start with the code. And then
Yeah.
after that, because Aisha also wouldn't take that long, we'll see who's got to present. And then, like I said, this might not be a full 3 hour session, but after we finish with this one, we'll come back next week and kind of wrap it up with that. Okay, cool. So Aisha, go ahead. Yeah.
Yeah, just 1 minute. Okay, you should be able to see the screen. Can you see the screen? Yes.
Yes.
Okay. So again, we are back to the patient MNIST dataset. And firstly, I just want to quickly recap what we have done last week and what we covered last week and what we're going to cover today. Last week, we looked at the patient MNIST datasets. And if you look at the codes, we had some functions which we defined to load the dataset for the plotting or for the train the model or to print out the matrix. And
here we defined our training variables. Those are the number of the classes, which is 10 class names. Those are listed here. And we define the epochs, batch sizes, channel, verbose, and the metrics. And then last week, what we did was we load the data sets, and it was calling the load data set, and it was returning us those uh, parameters. And then last week, aim was to build the perceptron, single layer perceptron model and the multi-layer perceptron model. And the different was to, yeah, last week we were using the TensorFlow, and we saw how is it done in the TensorFlow. Like we were instantiating the model by using the sequential, and we were adding the layers, and then we were compiling the model, and the summary function was giving us the details of the model. And then we trained the model, and we print the loss and accuracy. And we did the same thing for the multi-layer perceptron model. The only difference was adding the more hidden layers, and compile the model and train the model. And today we're going to look at the convolutional neural network. So you're already seen the convolutional neural network, I believe. And but just as a recap, is mainly used to work with the visual data and is mostly used in the robotics and the computer vision. First of all, we're going to discuss the convolutional layer. So I just want to show you this image here. Um, an image is just a matrix of pixel, as you know, and in CNN, um, so in the multi-layer perceptron, we were flattening the image, but in CNN, instead of the flattening the image, we are using the kernels or the filters to read the pattern of the data, to pattern in the image, and we have, in the end, we have the convolved features. And you might have seen the max pool, like we are applying the max pool to reduce the dimension and doing the max pooling, and we are getting the output. And let's go back to the code. And here we have the input neurons, and we are trying to read the pattern of the image, and we are getting the output here. And at the same time, we are reducing the dimension. So here we are creating the CNN model, and we have the parameters, image height, image width, and the channel, number of the classes, metrics, and optimizers is ADAM. These are the defaults parameters. And the first thing is we are defining the number of the convolutional filters, which is the 32. Then we are defining the kernel size, which is 3. And we are going to define the pooling area for the max pooling. This is 2. And then we are instantiating the model with the sequential. Then we are adding the convolutional layer. Of course, I've run all these codes, and I thought you're also familiar, and I did not go to the first section. But first of all, we are importing the let's come back to here first. So we are importing the libraries, and the second thing is we need to load the data sets, and the function was here for the convolutional neural network. And you can see here X-train CNN, Y-train CNN, test, image height, and width. And when we call the load data function, this time we are, as a first layer, we are choosing the convolutional 2D. And let's see what we are doing there. So when we go back to the load data function, The first thing is we are calling the load data, and these data sets was already in the Keras, and we are installing, and it's giving us this set of X-train, Y-train, X-test, and Y-test. And the first thing is we are printing the shapes, and then we get the height and weight, which is the 28 and 28. And if it is a perceptron, we were reading this part of the code, but now we are selecting the convolutional 2D, and we are reading this part of the code. And what it does here is it just the reshape the input variables, and before that it was 60,000 20 by 28 by 28, and last week we flattened it, but this week we're going to make 60,000 20 by 28 by 28 by 1. So that's the reason we have the 28 here, 28 here, and we have the channel, and then we also convert it to the float 32, and the same for the X test, and then we are printing the shape for the X train and X tests. And then the next thing is we are normalizing the values between the 0 and 1. And then we are converting the labels to the categorical by applying the one-hot encode. And then we are printing the number of the classes, and we are printing the label of the first image after converting the categorical. And let's see what is done here. Let's see the output. So before the reshaping, we have the 60,000 28 by 28, and for the test data sets. And after the reshaping for the X train, we have the 28 by 28 by 1, and for the test X test also we have the same. And just as a recap, so we have in the total 10 number of the classes, and before that it was categorical. Sorry, it was just a digit and 9, and we are converting to the vector form, and this is the categorical label. Yeah, and so we load the data set. I don't know why it's not going down. So yes, we load the data sets. So when we are so here was the definition of the function. We say that we define these variables, we instantiate the model, and we are creating the convolutional layer, and we are passing the number of the filters. The kernel size is 3 by 3, and strides, and activation function is relu, and because it is a first layer and we are defining the input shape, these are the image height, width, and the channel. Then for this sample, we are adding the batch normalization. And then the second thing is we are doing the max pool, and the pool size is here, 2 by 2. And if you want, you can uncomment this. You can add the dropout layer. And after we reduce the image to a certain dimensions, we are free to flatten it. And here we use the flatten. And the last one is we are adding the dense. And this is 128 output and the activation function relu. And then for the output layer, we are adding the number of the classes, 10. And we are using the activation function as a softmax, and we compile the model. And in optimizer, we are using the item. Then we call the function and we get the summary of the model. So here you can find the type of the layers, output shapes, and the parameters. And the last thing is we are training the model. So we are passing these parameters and we get the training results. Um, so we defined the 50 epochs, but it stopped in the 18. It did not see more than improvement and it went to the early stopping. So when we look at the accuracy and the validation accuracy, so when the accuracy is increasing, there is a difference between them. So we can try to work on that, and you can also look at the graphic, like the model loss and the model accuracy. But still, there is a difference. So we can try to make it as a better line by improving or by changing the batch sizes. Um, so this was the CNN model. And the second thing, actually, to demonstrate the Keras classifier, but looks like there is some error here. So, but I'm just going to explain to you and I will just update the code after fixing this issue. And this is another model, Keras classifier. And in this one, we want to use the grid search. And to use the grid search, we want to find the optimized parameters, like for the optimizer, which will be the best for us, for our model, which epoch will be best for our model, and which batch size will be best. So we are defining those optimizers, epochs, and batches. And then we apply these in the grid search to find the best parameters. And in the end, we are summarizing the results, like we are printing what is the best parameters. And then we can build our model based on these parameters. But like I told you, I'm not able to show the result to you right now, but I will fix it. We will fix it and we will update in the document as well. So this is the end of the session today from me. And there are two more models here, but we will cover them. We will cover them next week. So here we are doing we are building the K-means model, and then we are also building the Gaussian mixture models. I would suggest you to have a look at these models and make a note of all the questions, so that because these are quite complicated and quite long, and it will be interactive also if you make a note of your questions for the next week, and we will be looking at these two models, how we are building this.
So thank you for that, Aisha. So like Aisha said, that this time around we won't be giving you time to do this because we know that this particular code has some issues. However, we will fix it hopefully this week, and therefore you should be able to run it over the week. And the next week and the final week, we are going to cover, like Aisha said, the GM cost and mixture models, and I forget there was another one there. But
The Gaussian
we
mixture and K-means.
and the K-means, yeah, that's right, yeah. So
Sorry. Yes.
that's fine. Thank you for that. Yeah. So have a look at those modules from the notebook, and then you can post some questions next week, and then we'll cover those in the code next week as well. So next week again will be the sort of the summary of the different kind of just wrapping up for any questions and making sure we have any sort of things, and this particular session as well, this particular code as well. So I guess that's the only thing which we haven't covered so far. This thing which we will do next time. So now the question is, who has got anything to present? And so Aisha, have you finished now? Yes.
Yes, I can stop
Okay,
my.
thanks. Yeah, you can stop now. Yeah,
Yeah.
good, good. Okay, thank you for that, Aisha. So, oh, sorry, there's a question here or not? No, no, that's fine. That's not, that's with autoencoders. Yeah, that's fine. We covered that. Yeah. So, who has anything to present today? Okay, Sonal, yeah.
Yeah, I have finished the scikit-learn exercises 2 to 5, and I sent a message to Aisha that I can present that today.
Yeah, sure. Yeah, go ahead, please. Then, yeah. So you can
Okay.
start sharing your screen. Let me just make sure that you
Oops,
can
sorry.
share
I
your screen. Uh,
Yeah, I think I raised my hand by mistake. I'm trying to.
no, it's okay. Let me make sure that you can you share your screen or
I'll try.
yeah.
Uh, can you see my screen?
Yes, we can. Yeah, good. So that's working. Yeah.
Okay. Yeah, so this is the exercise 2 that we were supposed to complete, and it's mainly about standardization and normalizer. So the difference between I mean, I searched a little bit about the difference between standardization and normalization. Is what I found is like when in normalization we apply it across rows, whereas standardization is applied across against columns. Mainly when we want to compare two different features on the same ground, we use standardization, versus normalization we use especially when we want to change the distribution of our data. If we know it doesn't lie under the normal or the Gaussian distribution, which is a bell curve distribution, that's where we use normalizer function. Standardization is mostly used for when we want to send in inputs for example, for the neural network, where if we don't do that, the range in which the weights are configured would be a wider range, versus with after standardizing those inputs, it narrows down the range of the weights. So we're supposed to do that with the Boston data set. So this is what I've done. Here I applied like a standard, the scalar. I did a fit transform on the inputs, and then I did a describe, and imported the normalizer and did a fit on it and transformed that data. So that was exercise 2. Exercise 3 was about the metrics that we were evaluate to find the accuracy of a model. And I think the one that was being used actually was with recall, and we were supposed to do it with precision and F1 score. So precision is false positive upon true positive upon false positive plus true positive, I think. And the recall is true positive upon false positive. True positive upon true positive plus false negative. Um, and so we were supposed to like use that, and also the receiving operating characteristic curve, and we're supposed to like um, find out what that means. I found out like the receiving operating curve is mainly used for when we want to find like a diagnostic accuracy, or another application that I can think of is using lift curves to find how do we define a good pricing using a lift curve. And please correct me if I'm wrong anywhere. I'd like to improve my understanding on this as well as we go. So um, so the first part of the exercise was to use a cross-validation function with scoring as F1, scoring as precision. Um, so those are the ways how we can implement that. And then the second part was to look up and implement the ROC metric. So this is what we need to do to implement the metric is like import ROC and AUC and then score it. So typically with every scikit-learn library, it's very standardized, like you fit and then you predict. So that's what I did over here. I think I haven't ran the earlier cells today, so I don't know if this would work, but yeah, so it needs me to run the previous cells before I move on to this one. So I wouldn't take much time on that one. The next part is like multi-class regression problems, and I think it was again multi-class classification as well. So binary classifier is like when you have an presence or absence of something, we have a single output node, which is a binary. I mean, at least in terms of neural network, that is how we do binary classification. Multi-class classification is, for example, we want to predict something like a risk, whether it is from 0 to 5. What is the risk of something happening, or risk of tumor or something like that? Then that's a multi-class classification problem. So then we use like the evaluation metrics for regression problems would be an R square, mean standard error, mean absolute error, root mean square error. Those were the the answer to the evaluation metrics that could be used for regression problems. The next section was we had to like implement a baseline model and do an evaluation matrix on the Boston data set. So that was pretty simple because we had the other implementation similar to that, and we had to just do for the Boston data set. So again, dividing it into a train test split, using the linear regression. I'm using R square metric here, and then standard fit on that, and then scoring it. And that's actually the baseline score. And then when I do a predict and find the y predict and run an R square based on the actual values and the predicted values, is what I get as the actual score on the actual data. And then the same thing we were supposed to do after standardizing the data. So these are basically the same steps, but I applied standard scalar to the inputs before. And then these are the same evaluation, but I used a R square over here. So this is using the mean absolute and the mean square error on the same. So the next part 4 was classification and regression problems. And the exercise is that you have to fit and instantiate these machine learning models, and then research and into SVM decision trees and logistic regression. So SVM is support vector machines. It is mainly used to learn non-linearity. Basically, decision tree is gonna plot hyperplanes to separate the data, and basically it would split it based on certain features. Like, for example, you have input features like, for example, on the iris data set, we have like the petal length, sepal length, petal width, separate width. So those are some of the features based on which it would find how to separate each of these features. And then it will find the goodness of the split using either entropy or Gini. And then it's gonna create all these all the different trees. And then once it creates these decision trees, it would start pruning them and then give us the best decision tree at the end. So that is how decision tree is used. Difference between decision tree and support vector machine is that with support vector machines, it is more tend to do a non-linear split versus a linear split between the features. And please let me know if my understanding is wrong over there. Logistic regression is a simple classification. Regression is it's gonna like, so logistic regression is just a classification that we are doing, whether something is present or not. So this is, what I did with that data. So I kind of forgot what the other data set was, but other than the Boston data set, we had the other one. Sorry, the breast cancer data set. So we just want to find out whether the it is the output variable is whether it has breast cancer or not. So that is being used because this is a classification problem. And then on top of that, apart from the decision tree classifier and the logistic regression, I also use the Gaussian knife-based classifier, the ensemble, random forest classifier, and multi-layer perceptron classifier, the XGBoost, which is been very successful prior to neural networks, and gives quite a good accuracy, and the SVC classifier. So I did the same thing on, I don't want to take too much time, but I did the same thing. The procedure is kind of same for every of these, in scikit-learn makes it very easy on us to use these classifiers. So logistic regression, just a fit, predict, find the accuracy. Same thing for decision tree, same thing for random forest. But the accuracy that we get on each of these is pretty, logistic regression can, the accuracy with decision tree is many of the times better than logistic regression, and random forest is where it uses multiple of these decision trees. And so here I set the estimator as 100, which means it creates 100 decision trees to learn different aspects of the data, and then it creates an ensemble on that. The scoring I used in all this is to keep it standard. I use precision. With the decision tree, I used the criteria entropy, but I can even use Gini on it. It's just a different way of finding the goodness of a split. The last part was regularization. So, as it says here, we use it to prevent overfitting or underfitting, which is like basically we penalize, add a penalty term at the end of our equation so basically with L1, we use an absolute value of magnitude of the coefficient as the penalty term, which is the summation of beta j from j going from over the entire set, and multiplied by a constant lambda. And then for L2 regularization, we use the square of the magnitude of the coefficient. So the first part, L1 lasso regression, the same thing, fit. The alpha for that is 0.5. This is for ridge regression, which is L2 regression. This was already done. So the exercises we are supposed to do for using Elastinet helps us to combine L1 and L2. So we're supposed to Google and see how to use that. So that is what I've done here. So basically, get the model, score on that one for L1, the training score, the test score. Sorry. And here I've used Elastinet. We can so I tried with different combinations of alpha, like I used 1, 0.5, 0.2. And so with alpha, L1 ratio, as I start reducing it, it starts tending towards becoming more like an using directly an L2 penalty. As I start increasing that, so it tends towards becoming more like using an L1 regularization. So we can tweak that. We are basically like using different values. We can tweak that. Like for example, over here, if you see, these two, the first two values are when I used L1 regularization, and these two are when L2 regularization. So the scores better with L2 regularization. So using L1 ratio as 0.2 for Elastinet, these are the values that I get. But I got other values as well, which I have not, ran in this final run. Sorry. And then using grid CV, so just like we do a grid search CV, we can basically send it at a vector of values, and it's going to find out the best value for us, which is 0.76, which is very close to what we got over here. Sorry about that. That's all I have. Any questions?
No, thank you very much. That's quite impressive. And thank you for your good work with that, Somal, again. So no questions as such, not from me directly, but again, we appreciate your work. And this was partly the intention of it, to see how many people actually go through this and attempt to present at least part of it here. So regarding, also, you sent me a question, Sonal, separately by message, and I'm traveling next week, but I have asked Aisha to get in touch with you, and we will together help you out with what you have raised with us in terms of sort of what you want to do next in terms of learning to code, etc. Yes,
Sure. Thanks
sure.
so much
Thanks.
for
Yeah.
this opportunity to present, and I really appreciate your and Aisha's hard work on helping us learn. So this was a very good course. Thank you very much.
Thank you very much with that. So, like I said, I'm off to India. We are launching a new product, but I will, and Aisha is a part of that as well. And Aisha will be possibly easier to speak to next week, considering the time zone issues with that. Cool. Thank you for that.
Thank you, Sonal,
So,
for the work.
yeah, sorry. Yes, so go on, Aisha. Yeah.
I know. I just say thanks for the Sonal for her work.
Good, 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 good.
Thank you, Aisha. Thanks.
Yes. Okay. So, who is there anybody else who got anything to present? I mean, code. Yes. Yeah. If not,
No,
yeah. Sorry. Go on.
no, just one comment. Actually, I was going through that FMIST code, and thank you for that. I can see a lot of hard work there. But I was trying to understand by changing the parameter as a true, that was the assignment. And so that is a data augmentation. So in that, I have gone through it. I don't have anything to present, but I could see that for that, performance boost is there for this function. That is means in augmentation false in my machine. I don't know, that might be my observation. But data load took around 3 seconds, 31 seconds when augmentation was false, and when augmentation was true, it took 3 seconds. So was it a correct observation? And after that, I got memory error. I could not able to run the program first, but that was my question. Was my observation correct? And I will come back to you with the error details also.
Yeah, it's
Yes.
hard to. Sorry, Aisha. Please.
Yes, I think it is better if you just share your
Yeah,
home code so that I can just follow up what was going on and what you are
yeah,
doing.
sure,
It will be easy to comment on that.
Yeah.
I can present the Boston dataset regression.
Yeah, go ahead. Yeah.
Yeah, go
Okay.
ahead. Yeah. Sorry, who is this?
It's
Okay.
Vivek.
Yeah. Okay. Yes, please, Vivek. Go ahead. Yeah.
So, can you all see my screen?
Yes, it's coming through now. Yeah.
Okay, so the Boston dataset regression initially, as I shared, it was done with SVR model,
SVR. Yeah. SVR.
SVR model. And then the exercise was to use linear regression model. So what we will do here is we will just compare how these two models worked side by side. So in SVR model, uh, I'm not going through the initial things like loading the data and pre-processing the data, but here is the place in the code where things change. We change the model to linear regression, and then evaluating the model. Let's see what's the difference that we get. With SVR, we were getting R square value of 0.66, and when we change it to linear model, we get relatively higher R square value. So apparently this model fits better for the data, which was surprising for me because I would assume SVR is more complex in nature compared to linear, but still. And then after improving the model, when we get the best parameters, C equal to 10 and kernel RBF, for SVR, this R square is increased to 0.87, which is quite impressive. But in the linear model, I tried to get the best parameters, and I tried to see the documentation of linear regression, and I found that uh, I found a few parameters like fit intercept positive and copy X, and then I got the best parameters. I entered those best parameters, and apparently the R square value was still the same, 0.78. So what I think is that initially when it implemented the linear regression model, it already chose the best parameters. So after the improvement, the parameters that I set were same as previous. And that way, what I found was that you can improve the SVR model uh, using by adjusting the hyperparameters. In the linear regression, there is not a lot of scope for improving the model, and that's what I learned. But if you think I did something wrong here, please let me know. That's it.
Thank you, Vivek. I think you did everything right. Just that we need to deep dive into the code and try to find out why it happened or why we are getting these results. It's just a matter of exploring more.
Mhm. Sure. Thank you.
Ajit, we can't hear you if you're speaking.
Yeah. Shall I show my error,
Can you
Aisha?
can you hear now?
Yes, we
Yeah,
can
sorry,
hear
I don't know
you.
what happened last time.
No,
I
no,
was
no.
trying to speak something. Yeah, sorry. Yes, yes. Thank you for your effort, Vivek. And like Aisha said, we will definitely come back to you. But like I was trying to say, which I don't think I could say properly because there was something wrong with the headset, is that there's no right or wrong answer. We really wanted you to make the effort and learn something and implement it in a different way. And I think that definitely you have done, and I appreciate that. Thank you for that. Okay. Good. Okay. Sorry. Nitin, I wanted to present next Sunday. Yes. Okay. Sure. So, Nitin, thank you. Yes, please. You can present next Sunday. So was somebody else saying something here?
No, just wanted to show my error when I tried with data augmentation tool.
Okay.
Is
Yeah,
it
you can share. You can share because at the moment nobody's sharing, so you can share your screen.
okay? Let me know if you can see my screen.
Yeah. Yes, it's coming through.
Yeah. So here, as per the assignment, I changed the data augmentation equal to 2 in fmist. So not sure. This is the when I try to run this one. This train model.
Mm-hmm.
Yeah.
So all you did was only changing the data augmentation from,
data augmentation. Yes. Yeah.
and you did not do any other changes, right?
No, no, no. I think so. I think it might. I will. I think I have saved the error also. Okay. here. Yeah. PRA. Don't know why it's giving some augmentation error also, and the program stops here. But I could see that the data load performance got boosted by using data augmentation tool. That was my observation. So here in single layer perceptor model, it's failing. Maybe I will send you the details. Means I should don't want to waste all of us time.
Yes, yes. If you only change the data augmentation, I can just give it a try and see
Okay,
causing the issue.
sure. I just changed that only.
Mhm. Okay.
And anybody can take it over. I'm done from my side. I will share you the details, Aisha. Anybody can take it over.
Okay, yeah. Just ask you, send your questions as well, what you wanted to point out, and so that I can also focus on your questions.
Yeah, sure.
Is there anyone who wants to present?
I was able to load the fashion and NIST code, but I'm unable to interpret the results. Can you help me with that?
Which results? Yeah.
Fashion MNIST. So we are supposed to, I mean, the algorithm is supposed to tell you for each image which category it is in, right?
Yes. Yeah.
Yeah. So I mean, I'm getting the results in the form of, I don't know, it kind of k-means. So how do I interpret that? I can share my screen if that
Yes,
is.
maybe it is better.
Yeah. So it took me a long time to load this, but it worked. This step took really long fitting the model. And then this is the training and validation epoch graph that I'm getting.
Yes.
And then this is,
So you're asking for the k-means and Gaussian mixture model part. So I think it is better we cover this next week, as we mentioned in the beginning. So we're going to.
okay.
And you can also prepare your question for the next
Yeah.
week's.
Yeah. And also the reason for next week is we are going to hope to get Kautar back on next week as well. So that way also we can cover up any questions which we have, and that being the last session.
Yes.
Very good. So thank you.
These two models will be covered next week, k-means and the
Mhm.
Gaussian mixture model.
Sure. Thank you.
Good. And also, Nitin, you want to present? Thank you very much. Ridwan, you want to present next week? Thank you very much. So both of you are presenting next week, and this is perfectly fine. Again, this is like I said, there is no right or wrong way to do these things. It's just that it will help from your perspective to learn that. So next week I'm traveling a little bit, and I think that I will try to make the time, but I might be delayed a little bit. But in any case, you have both Aisha and Kautar with that. So Farid, yes, please. Yeah.
I had a question which I'm not sure got answered. It was to do with scikit-learn. I couldn't get the stratify to work with the Boston data set. Maybe I've misunderstood, but could you?
So where was the question you placed? Was it on the chat? Was it on the channel?
Question, I think it was on the third. So
So it was on
Oh,
the Slack. It was on the Slack. Yes.
yeah, yeah,
Okay,
yeah.
that's fine. That's fine. We'll go through that and try to wrap up the questions. But that will be the other goal for next week as well. We'll go through all the questions in Slack and try to find out between certainly Aisha and Kautar will go through it over the week
Okay,
and try to find out with that.
okay,
Okay,
thank
cool.
you.
Perfect. Thank you very much. So in this case, if there's nothing else, we'll wrap up now because I think next week at least three more people want to present. So Ridwan, Nitin, and I think somebody else. I forget Vivek as well. I think so. This is good. I think that's our goal, and we'll wrap up next week with a few more questions. Aisha, do you want to add anything more?
No, I did all is fine. And just wanted to mention one more person submitted the assignments to me. I'm not sure I'm calling the name right or wrong. Vaishali or Vaishali?
Vaishali.
Vaishali, yeah.
Yes. So Vaishali is online, isn't it? I can see her. Vaishali are online.
If she wants to present anytime today, next week.
Yeah, I think let me just see how I find out who is online here. Vaishali, yeah, you can present next week as well because I know you've been contributing quite a bit to the course. So if you're online, let me see if you're online or not. Um, no, yes, you are online. Yes, no, you're not online. I think Vaishali. There's another Vaishali here.
Oh, okay.
Yeah.
Which one submitted to me is Arjun.
Oh yeah, no, okay, that is Vaishali. Then that's right. Yes, says Vaishali. Yes, of course, Vaishali. She can present next week. Okay, you are right. I show you're right. Yes, so it is the
I
same
mean, if
Vaishali.
she wants,
Yeah, no, that's fine.
she
That's good.
already
Okay.
submitted. Mhm.
Thank you very much again for all your help, and thank you especially the people who presented today because this was our objective, that we wanted to get you actually doing something and presenting something because, like I said, it's 8 weeks. It's quite a long thing, but we thought that it's better to go through it in a little bit of depth rather than just rushing through, as people sometimes do, and then you end up knowing nothing. So in this case, at least if you know at least 50% of it or something like, and if you actually made the efforts to present something, you definitely will get a lot from this work with that. So thank you, Aisha. Do you want to add anything more?
Thank you all, and thanks for all your work. And we are waiting for your edition also next week. And it's great to see your
Yeah,
edition.
maybe, shall I ask one, maybe a basic question?
Yes.
In yeah, FMIS program, the confusion matrix, right? We have 10 classes. So in which, can you explain what is this output means? We are representing the highest possibility or with the number which is near to 1. So we are highlighting that number in the confusion matrix. So
Uh,
if you want, I can share my screen
Sorry,
quickly.
are you asking for the
Yeah, yeah. So, uh, so in this one, if you can see my screen.
Yeah, so confusion matrix is basically a 10 by 10 matrix because you got 10,
Mhm.
yes,
10
0 to
classes,
9.
yeah.
Yeah. Sorry. Yeah, so what is the question?
Yeah, so actually my question here is, Miss, I was expecting that from the images we are going to count or we are going to find the classes or the type of object. So what is this output predicts? How to read this output?
So it shows that how the features are correlated with each other. Um, from the dark to the light, it shows how strongly positive in a positive way or in a negative way. It shows you the
Okay.
correlation between the features.
Okay, so it means the ankle boot is 0.97, and so it means it is much darker than the t-shirt. Is
Uh,
it? Shall we read that way or?
I can't see the probabilities properly, but yes, if it is darker, yes, it is more correlated than the others.
Okay, so that is our aim of this MNIST, FMIST, this one program to find out.
Yeah, but remember that the confusion matrix is just showing the correlation. Yes. So in the end, you are doing a classification. You're going to
Hmm.
classify which class it falls in. But here you are trying to do the correlation between them.
Okay.
Yes. Okay. Very good. Okay. Thank you very much. So again, we see each other next week. And yeah, thanks very much. Okay.
Yeah.
Thank you.
Okay. Thank
Thank
you.
you. Thank you
Bye-bye.
very much.
Bye.
Very
Bye.
much.
Bye. Bye.
All the best.